The hook for today has to do with putting this large weight up on your roof and knowing how strong the joists are, what load they're capable of supporting. And the question is, are you going to get into trouble? This would be an important engineering question, an important architectural question. If you were doing this yourself, you would want to know the answer before you got it up there. I don't think that you will be in a place to do this problem, but you will understand the concept of doing this problem by the time we're done with the lecture. It turns out that it would work. However, if the if the weight got up to this amount, at that point you would start to have your joists fail. So you did not have a lot of free space in that calculation, but an important calculation. I want to know how to do that. And it really comes down to understanding how to work with vectors. And you recall that a vector is something that has, and the people all say size and direction. And the important thing is that that is all that they have, just size and direction. We represent a vector with an arrow, which nicely captures the size by how long we make the arrow. This would be a smaller size than that one. And its direction by what direction we point the arrow. What a wonderful metaphor that arrow is for this idea of this thing that has size and direction. Only size and direction. In particular, it does not have location. So this vector is exactly the same vector as that vector, and so is this one. That where you draw it doesn't matter. As long as it has the same size and direction, it is the same vector. And you will do a lot of moving vectors around. And when you do so, you must preserve the size and direction, or you are not working with the same vector anymore. Now, on your sheet, I would like you to make a vector called H, which goes up towards the top of the worksheet and has length of about 3 centimeters. That's 3 narrow pinky widths that it goes up. Doesn't matter that you get it exactly. You just draw a vector on your piece of paper. And then what I would like you to draw on the worksheet is a vector which you would identify with 3H. And I say no more about it. Please do that. Stop the show. When you've finished doing it, then start the show again. And I would hope that what you had drawn was a vector like this. Where you draw it, of course, doesn't matter. But it does matter that it be going in the same direction as H and that it be 3 times as long. Because when you did that, you showed an intuitive understanding of vector addition. That you took 3H to mean 3 times H, but what 3 times H means is H plus H plus H. And if you take 3 H's and stand them on top of one another, that is how you add H plus H plus H, and this vector, which goes from the tail of the first to the head of the last, is equivalent to H plus H plus H. And that's how you add vectors. You move them, preserving their size and direction so that they are head to tail. And their sum goes from the tail of the first to the head of the last. I'm going to do this. You can just watch and admire, but here you have these 3 vectors. I would like to add them together. Well, I choose to start with the blue vector, and I could leave it right where it is, or I could put it in a new location. and then I will choose either the red or the green and put it head to tail. Now I could have put the head of the red at the tail of the blue. And then the last vector I will put to the only available head. That head is occupied. I will put its tail, and the resultant goes from the tail of the first to the head of the last. And we don't call it the sum. We do indeed call it the resultant, because suppose this was 2 long and that was 3 long and that was 2 long. 2 plus 3 plus 2 adds up to 7. But that vector's length is not 7. It's maybe a little bit longer than this one, which had length 3. So to avoid that kind of confusion, we don't use the word sum, but instead we speak of the resultant. But please note, if instead of starting with the blue vector, I had started with the red vector, and then added on the green, and then the blue, I get exactly the same result. If I start with the green, and then add on the blue, and then the red, I get the same result. That vector addition is commutative. It doesn't matter the order in which you add them. In fact, if you have something which has size and direction, and its addition is not commutative, then it's not a vector. Just to hammer it home that there is this logic to what we're doing, suppose I said I would like you to make these 3 trips. Walk 2 blocks south, walk 3 blocks north, walk 2 blocks east. I want you to do those 3. Do those 3 things for me. Add them together. Well, I think it is rather obvious that what you would do is first do one of the journeys, and then to add on the next journey. You would not go back to where you started from. If you're adding it on, you would take the first journey and you would add the second journey onto it. That head to tail construction. And if you're going to add on this third journey, you would take where the first 2 journeys had got you to, and that is where you would add on the third journey. And that displacement is equivalent to this displacement, going from the tail of the first to the head of the last. Now I want you to again take that vector h that you've already drawn, and you can probably just use that same h that you have on your worksheet, and I want you to draw a new vector called g, which instead of being 3 pinky widths is 4 pinky widths, going off to the left. And then I want you to add the 2. Go ahead and do that, and then start the show again. And it should have been that you either put G at the head of H, or you put H at the head of G. It didn't matter. And you did not stop at this point. That's good orientation for adding H and G, but you're not done. It's like I asked you to add 3 plus 4, and so you wrote down 3 plus 4. I would be very upset with you. No, you have not done the task of adding 3 plus 4, and you have not done the task of adding H and G until you have indicated for me what the equivalent vector is, the resultant vector. Again, note that if you add them in the opposite order, that you do get the same result. Done. Okay, now I would like you to do these problems C and D and E and F on your worksheet, but I am going to do C. I would like you to do C first, then stop the show. Stop the show while you do C first, and then you start it again. And what you might have done was to put the red vector at the head of the blue vector, or you might have put the red vector at the tail of the blue vector, but always head to tail construction, and the resultant goes from the tail of the first to the head of the last, from the tail of the first to the head of the last. It didn't matter where you drew it. You should have gotten a vector which was pointing in this direction and had that length. Okay, go ahead and do D and E and F, and you will have practiced enough. New topic. I'm going to start with the resultant, and I'm curious to know what two vectors add up to this vector. And it might seem obvious to you that a pair of vectors like this add up to it. But you would be curious to know that that's not obvious to everyone. And in fact, it's not the whole story. But these two vectors, which add up to this vector, are called the components of this vector. The things that make it up, the components. But note, these two vectors also add up to the purple vector. And so do these two vectors add up to the purple vector. There are infinitely many pairs of components which add up to this purple vector. And so in the context of your particular problem, you would want to choose the pair which work, which provide the information you need to have. Note also that this pair of vectors also add up to the purple vector. And that pair I am not interested in. It turns out when I say the components of a vector, what I really want are the perpendicular components. These two are components, but they have no use to me in problem solving. So when we talk about components, we always mean a pair of components which add up to the vector and are perpendicular to one another. Not to the vector they're adding up to, but the two components are perpendicular to one another. So here you have a problem. Here is a vector. I want to break it into components relative to this direction. Maybe that's the roof. And some people, that's an easy task to do. But for those of you for whom it's not an easy task, I offer you this mechanism. Take a pencil and put it on the paper so that it is parallel to that direction. And do it far away. Put a pencil down. And then slide the pencil in until it touches one or the other end of that vector. This gives you a sense of one component is going to be going along this direction, coming out at the head of that vector. Then take your pencil and put it down perpendicular to that direction. And put it far enough away that you don't get confused by that thing there. And then slide that pencil in until it comes out at the other end of the vector that you're trying to break into components. This then should provide you with a structure where you can see that you would have a component like this, or something like that. That seems a little bit off, and a component like that. And those two peach-colored vectors are components of this, relative to this direction. One of them parallel and the other perpendicular, and they are necessarily perpendicular to one another. So, perhaps with that instruction, you are ready to do these three. Again, I'm going to do the first one, just in case you need a little bit more instruction. You can stop the show. Please do this problem. And then when you start the show again, I will show you my doing it. And I have one vector which is perpendicular to that, and I could either draw it so that it touches the head or touches the tail, doesn't matter, and another vector which is parallel to this. And once I have made the choice of having the other one touch the tail, this one has to go to the head, and there you have a pair of components, perpendicular components, for this vector relative to that direction. Here I have a train car on a track, and I have already broken them into components parallel and perpendicular to the track, but I just point out to you that here you can see that this is the car that is going to accelerate the most rapidly, and this is the car that's going to accelerate the least rapidly, and we can see why. The component of its weight is small here. The component of its weight is the largest of the three here. And so this will produce a lot of acceleration. This will produce a little acceleration. If you made this perfectly flat, then this component would be 0, and the car would not accelerate at all. It would stay sitting there in equilibrium. Okay, new topic. I want to find the height of this tree, and I can't climb that high. I don't have a rope long enough to hang down. So what I do is I measure some distance away from the tree, find what angle I have to look at to see the top of the tree, and then I make a little model of that situation, a scale model with the same base angle and the same right angle here, so that the big triangle, capital A, capital B, capital C, and the little triangle, lowercase a, lowercase b, capital C, are similar to one another. And when you have triangles that are similar, their sides are in the same proportion, and so BA is to AC as BA is to AC, and from that ratio I can put in this length and these two lengths, and I can calculate how tall the tree is. Lovely. So wonderfully lovely that instead of making little models every time I want to figure out how tall a tree is, I made this whole mathematical process called trigonometry. And we give the name to the ratio in a right triangle of the opposite to the hypotenuse. We call it the sine, and the adjacent to the hypotenuse, we call it the cosine, and the opposite to the adjacent, we call the tangent. And you have this wonderful mnemonic, SOHCAHTOA, and you are going to do this all year long. So if you don't feel comfortable with this now, you might as well get comfortable with it in a big hurry, because you're going to be doing it all the time. Okay, so now we're back to that adding h and g, but now I can do it mathematically. That if these two are at right angles to one another, then I can use Pythagoras to get how long that vector is, its magnitude, and I can use trig. I can take this angle here and say that that's the angle whose tangent is 4/3, and the angle whose tangent is 4/3 is 53 degrees. And so I am able to say that the sum of 3 north and 4 east is a vector equal to 5 at 53 degrees east of north. We could have also given the direction this way, but notice I have given the size and direction of the vector. I would point out that 53 east of north is the same thing as 37 north of east, and so those two angles, 5 at 53 east of north and 5 at 37 north of east, are the same. And I hope you feel comfortable with this. You're going to be seeing it a lot, and I hope you will give your answers to me in that form. Notice what we do. It's backwards to the way it's written. What this means is start at north and then go east of it by 53. Or start at east and then go north of it by 37. Get good at that. Okay, again, I'm going to add 3 and 4. Uh-oh, but now they're not at right angles. What do I do in such a situation? And what you do in such a situation is to break the 4 into components which are perpendicular to the 3's direction and parallel to the 3's direction. And if this angle here is 120, and this now has become a right angle, then that angle there is 30. And so these components are going to be, this one here is going to be equal to, that's the sine of 30. The sine of 30 is equal to this component over the hypotenuse. So you do a little algebra and we get that it's 4 sine 30, which if you plug it into your calculator is equal to 2. And this one here, it would be the cosine of 30 is equal to x over 4, or x is equal to 4 cos 30, 3.5. Now I can take the 3 and add the 4 on, but add it on as 2 plus 3.5. That's the same thing as adding on that 4. And 3 plus 2 is 5. And now I have a right angle between the 5 and the 35. The magnitude of the resultant would be the square root of 5 squared and 3.5 squared. And the direction that it's going would be the inverse tangent of the opposite over the adjacent. So that would be 35 degrees east of north. Ah, lovely. Thank you.